Hi guys. Let's try to talk about second order linear differential equation. Okay. In the class, I explained all the detail how we derive like the general solution form of the second order linear differential equation. But in this video, I'm going to try to summarize everything very shortly. Okay. It is very easy to use the technique. Okay. First of all, this is only working for the second order linear differential equation with constant coefficient, which means the coefficient function must be constant only. It's not a function of t. Okay, and okay, so like at the first time we're gonna talk about homogeneous equation only. Okay, that's it. So as we talked about it, like for the second order linear differential equation with constant coefficient, and you can use the characteristic equation. We have to use the characteristic equation. Okay, and we talked about where this came from. Okay, and for now. And now we just accept whenever you have a second order linear differential equation with constant coefficient, and we're gonna use characteristic equation, okay? Then look at that. A y double prime plus b y prime plus c y is equal to 0. It is homogeneous second order linear differential equation with constant coefficient, okay? And um, like AR squared plus BR plus equals 0 is your characteristic equation, and which is quadratic equation, okay? And there are three cases. The first one is when you have like two different real number solution for this one, okay? The second case is, it was first one. The second one is when you have two different complex solution, okay? And third one is repeated one, okay? So we will talk about these three, okay? The first case, when you have two different solution, then your solution, two different real root R1 and R2, then your general solution is this form, linear combination of exponential function with R1 and R2, which is a C1 e to the R1t plus C2 e to the R1t, okay? So R2t, okay? Let me give you one example, okay? It is really easy, right? Look at that. That is exactly second order, homogeneous second order linear differential equation with constant coefficient, okay? Then we will use the characteristic equation, which is R squared plus 3R plus 2 equal to 0. And it is easy to factor, right? It is R plus 1 and R plus 2 is equal to 0. So we have like two different real roots for this, right? Minus 1 and minus 2. And that's it. Then you can write the general solution for this differential equation, which is yt is equal to c1 e to the minus t plus c2 e to the minus 2t. That's it, okay? If it is initial condition problem, then you can find C1 and C2, right? And the next case, as I told you, when you have like two different complex root from the characteristic equation, okay? Then your solution form must be this one, C1 e to the lambda t. We assume like your two different complex root is lambda plus I mu and lambda minus I mu, okay? Then your solution, general solution is C1 e to the lambda t cosine mu t plus C2 e to the lambda t sine mu t, okay? And let me give you one example, okay? Here we go. Look at that. It is homogeneous second order linear differential equation with constant coefficient, right? Then characteristic equation R squared plus 2R plus 2 is equal to 0. We should use the quadratic formula, right? R is equal to minus B plus a minus. Let me write it, okay? Just want to make sure you remember this formula, right? Minus B plus a minus and square root of B squared minus 4AC over 2A, okay? And minus 2 plus a minus and square root of minus 2 squared minus 4 times A times C over 2 times A, right? Let me simplify. That is equal to negative 2 and plus a minus and square root of negative 2 squared is 4 minus 8, which is negative 4 over 2. That is negative 2 plus a minus 2i over 2. So it's minus 1 plus minus I. So this case, minus 1 is lambda and 1 is mu. Okay, let me write for you, okay? lambda is -1, which is the real number part, and mu is imaginary part, right? And that's it. Then you don't have to worry about the theory, but like you have to write the general solution directly, okay? Your yt is equal to c1 times e to the lambda minus t times cosine mu t plus c2 e to the minus t times sine of mu t. That's it, right? Is it easy? Then the last one is repeated root, right? Here we go. Since it is repeated one, okay. Since it is repeated one, and you will have only one exponential function, right? But keep that in mind, since this is the second order linear differential equation, you must have two particular solutions, right? And the other is a simple thing, just multiply t, that's it. So your solution form is c1 e to the rt plus c2 t times e to the rt. That's it, right? So look at that. It is homogeneous second order linear differential equation with constant coefficient, right? Then we start from characteristic equation, okay? 6r plus 1 equals 0. Then that is perfect square form, right? 3r plus 1 squared equals 0. So I have only one r, which is negative 1/3, which is repeated one, okay? Then what is your general solution? It's easy, right? Yt is equal to c1 e to the minus 1/3 t plus c2 t e to the minus 1/3 t. That's it, okay? Even we spent like, about 2 hours to go over like all these things, but like it is very simple thing, right?